Hello, AP Chemistry. How are we doing today? Hopefully, y'all are doing well. Today, we are going to be continuing our Unit 7 notes on equilibrium, and we are going to be covering solubility, equilibrium, and this is going to be part 2. Now, last class, we did start those solubility equilibrium notes, and we talked about 2 of the 4 main types of KSP problems. Now, as a reminder, what is KSP? KSP is going to be that solubility product constant. And so what we learned last class is basically using those equilibrium expressions, we can solve for our molar solubility, okay? And last class, y'all did work on being given 2 different ways, or those 2 different KSP problems, where the first one was if you're given the molar solubility, solving for your KSP, and then the second one would be the opposite of that. So given your KSP, solving for your molar solubility. So today we are going to be continuing those notes and covering the 2 new or 2 final parts of the solubility equilibrium, those 2 different types of problems you could see. So let's go ahead and get started on this. So the third type is that if we're given KSP, we can solve for the molar solubility in the presence of a common ion. So this does sound very similar to that very first one that y'all did, or the second type that y'all did last class. However, there is something different about it in that we are talking about in the presence of a common ion. And so basically when we're looking at those common ions, we're saying, okay, I've got a solution with, in, for instance, example 1 here, a solution with sodium iodide. And we want to add some lead iodide to that. So what would be the molar solubility of that lead to iodide? Well, since we've already got an ion, a common ion, specifically that iodide in there, that's going to change how much of that lead iodide can actually dissolve. And so this idea of this common ion, this ion that is the same in both of those compounds, we are going to be seeing how that's going to affect our solubility. Okay? Now, let's go ahead and dive on into this problem. So it says, what is the molar solubility of lead to iodide? And they tell us the KSP is 6.5 times 10 to the negative 9 in a 0.050 molar solution of sodium iodide. Now, it is important that you know what each of the compounds you have are. So in this case, I've got sodium iodide. Over here, I've got lead 2 iodide, which would be Pb with a +2 charge. Iodine's got a minus. So when you cancel those out, you get PbI2. Okay. Now, we need to figure out what is, or how this common ion is going to affect our solubility. So it's going to be very similar to what we did last class, but there's a little bit of a twist to it. So we are going to need a Rice table. So R, I, C, and E. And for this Rice table, we're going to start off with our reaction. So basically, I took some lead iodide and I dropped it into this solution that has sodium iodide in it. So really, in the grand scheme of things, what's going on? The lead 2 iodide is going to be dissolving into the sodium iodide solution. There's going to be 2 of those. Okay, so we're taking and we're looking at this compound, this lead 2 iodide, and we're going to see how its molar solubility is affected. So first off, I've got my reaction there. Now, I need to see what effect this has. So my initial, again, my lead iodide is a solid, so we don't take it into account when we're talking about those equilibrium expressions. I know that I start, my initial lead is 0. Okay, now here's the thing though. Since I'm dissolving this lead iodide into a sodium iodide solution, I actually have some iodine present in this solution, right? And so because of that, I do actually have to keep that in mind. I know that I actually start with a concentration of 0.050 moles, or molarity, of that iodine in the solution. Why? Because that is coming from this sodium iodide solution here. Now, here's something I want to note, is that if I had something like magnesium iodide, where I've got MgI2, then I would need to make sure that my concentration reflects that coefficient. so I would need to double my concentration there. So now I've got that. Now, if you see, that does make a small difference in terms of the overall change it might have happen. We're going to be starting with some more iodine, and as a result, we're going to see a difference in our overall solubility. Okay, so I've got my initial there. So my change is increased by x, increased by 2x. So my overall at equilibrium would be x here, and then it would be 0.050 plus 2x. So now let's actually take a look at solving for this problem. So the very first thing that I need to do now that I've got my rice table done is to write the equilibrium expression here. So I have my KSP. It equals the concentration of lead times the concentration of iodine. And the iodine is going to be to the second power because of that coefficient. Then I'm going to go ahead and plug in what I know. So I was told that my KSP is 6.5 times 10 to the negative 9. My concentration for lead is X. And my concentration for iodine is 0.050 plus 2X. And we're going to square that right there. Now, here's something to note. My KSP is a very, very small number. And so I can make the assumption that over here, this is negligible, and so it can actually be taken out of my equation here. Now, I'm just going to go ahead and solve. So I get 6.5 times 10 to the negative 9 equals 0.050 squared gives us 0.0025. X, divide both sides by that number. And we'll find that our X equals 2.6 times 10 to the negative 6 as our concentration. And since we are talking about the lead, it is a 1:1:2 ratio. That lead is going to have the same concentration right here. That's lead to iodide. And so that would be the molar solubility of my lead to iodide. Okay? All right. So now I want y'all to go ahead and give this next one a try. So pause your video, solve through the problem, and then resume your video and we will go over it. So here is what you should have ended up with. So you should have had 6.4 times 10 to the negative 8 as your final answer for that molarity, for that solubility of solid KF2. So going through it, first thing you needed to do was do your rice table. So your reaction was CaF2 in a reversible reaction produces Ca plus 2 plus 2F minuses. We know that my CaF2 is not taken into account because it is a solid. I'm going to go ahead and put that there. We started with 0 for my calcium, but our fluorine ions, we did have 0.025 of those. Our changes X and 2X. The equilibrium would be X and for calcium, and then for F minus, it would be 0.025 plus 2X. I can make the assumption that that 2X is negligible because our KSP is such a small number. And so after plugging in all my numbers and solving with my equilibrium expression, I am going to find that 6.4 times 10 to the negative 8 is my answer there. Okay. So I'm going to leave this next one as practice for y'all to do. So I will leave that on the key. Now, in this case, you are going to have to solve it multiple times because if you look, you do have two different KSPs there that you're going to have to work with. So I'm going to let you solve that multiple times and get your answer. But otherwise, we are going to go ahead and move on. Okay, so the very final way that we can ask for a KSP problem is, will a precipitate form when these two solutions are mixed? And so basically what we're doing is we're looking, if I take a chemical reaction, I mix two substances together, they're trying to decide whether or not a precipitate will form. Now, one of the things that I do want to remind you of, and we talked about this last class, is that if we're talking about determining whether or not a precipitate is formed, we do know that if our product ends up being greater than our KSP value, then what we can find is that that precipitate would form. If it's less than, we would have an unsaturated solution, and so we would not see the precipitate. And then if it is equal, we would have a saturated solution, but we would still not see that precipitate. All right? So let's take a look at this problem. So it says exactly 200 milliliters of 0.040 molarity BaCl2 are added to exactly 600 milliliters of 0.080 molarity K2SO4. Will a precipitate form? And then they tell us the KSP of BaSO4 is 1.1 times 10 to the negative 10. Okay, so what do I need to do first? Well, the very first thing that I want y'all to recognize is that my volume here has changed. When I take those two and add them together, that volume is going to increase. Well, what happens to our concentration when we increase our volume? If your volume increases, your molarity will decrease. All right. And so we actually do have to solve, first off, for the new concentration once those two are mixed together. So we're going to have to do a dilution problem when we do this. So remember, for dilutions, it's M1V1 equals M2V2, which when we solve for this, when we rearrange this equation, we're solving for M2. So we're going to get M1 V1 over V2 equals that new concentration that we're going to be working with. All right. Okay. So the very first thing that I need to do before I do anything else is solve for that new concentration. So it says exactly 200 milliliters of 0.040 molar BaCl2. So for BaCl2, I've got, so M1 would be 0.040 times V1, which is, we started at 200 milliliters, divided by my final volume. So my final volume is actually 800 milliliters. Okay, so I take that, I plug that into my calculator, and I find that my new concentration is 0.01 M for BaCl2. All right. Now I need to do the same thing, but this time I'm going to be doing my K2SO4. So my K2SO4, my initial concentration was 0.080 times its initial volume divided by the total volume. And what we're going to find is that our concentration here is 0.06 molarity for our K2SO4. Okay. Now, will a precipitate form? And they ask us specifically about BaSO4. So one thing to note is that this is a double replacement reaction, right? So basically we took BaCl2 plus K2SO4, and it produced BaSO4, and then it also produced KCl. So do we need all of that? Well, no, we really don't, because we've got our formula, BaSO4, and we know that as a result of this, we're going to get a barium ion and a sulfate ion. Okay, so we can go ahead and write our equilibrium expression here. And this time we're actually solving for Q. Now, why are we solving for Q? Because remember, Q is talking about that initial amount, right? So it's talking about before we have reached equilibrium. So here I've got Q equals the concentration of barium times the concentration of sulfate. And I need to know what I've got. Well, looking at my initial over here, for barium, there's one barium for that concentration, right? And for my sulfate, there's one sulfate in that concentration. So I can just go ahead and use those concentrations as my concentrations over here in my Q expression. So my Q equals 0.01 for my barium times my sulfate, which was 0.06. And so I plug that in, and I find that my Q is going to equal 6 times 10 to the negative 4. Okay, so what do I do with that? Well, I know my Q is 6 times 10 to the negative 4. I was also told that my KSP is 1.1 times 10 to the negative 10. Okay, and again, that came from my problem here. So 1.1 times 10 to the negative 10. So looking at my numbers here, I find that my Q is greater than my KSP. And if Q is greater than KSP, we know that we are going to be shifting that reaction to the left. So we're going to be creating that precipitate. We've got more in it that we can actually dissolve. So yes, will a precipitate form? Yes. Reaction will shift to the left to create a precipitate of BaSO4. And then this right here would end up being my answer. Okay. All right, y'all. So I want y'all to go ahead and solve this next problem. So pause your video, solve your problem, and then we'll go over it. All right, so what we should have found is that yes, because your Q is greater than K, the reaction will shift to the left to create that precipitate SRF2. All right. Okay, y'all, this final problem here. Now, before we actually do that, so for shortcut alert, so this is actually something that can help you when you're taking your AP exam or when you're taking the exam in our course. In a problem involving a dilution, just like the previous two problems, the volumes are often equal. So if that's the case, when their volumes are equal, so let's say they've got 500 milliliters of, what did we have in this last one? 500 milliliters of sodium fluoride, and then they also had 500 milliliters of that strontium nitrate. If they are the same, or equal to each other, then we can basically just take those concentrations and half them. Why? Because we're basically dividing it by 2 if that's what we're doing, right? And so in this example here, so for example, if 400 milliliters of each solution is present in the problem and they were combined, the resulting concentrations would be, in this case, 0.0400 divided by 2, which is going to give us that 0.0200 molarity. And then for the sulfate, it's going to give us 0.0800 divided by 2, which is going to give us that 0.0400 molarity. So it's just a shortcut for y'all, just to kind of help y'all with that. So if you're doubling your volume, essentially, you're going to be halving that concentration. Because remember, when your volume increases, that concentration is going to decrease. Okay. Very last problem is a challenge problem. It is entirely optional, but I do think that it's kind of a really a brain turner here. So I do suggest that if you can, go ahead and give this a shot. I'm going to put the answer on the key so you can double check that. But y'all, that is it for the lesson on solubility equilibrium. As always, let us know if you have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.